This video demonstrates the design process followed in order to make an aerospace component and the testing carried out for it to meet structural requirements. It provides demonstration of the use of Excel, CAD software and structural theory in order to conduct the design and manufacture of a component. Structural theory assumed for this project is that the spar is modelled as a uniform cross-sectional beam with a triangular distributed load. This is the design process followed by engineers in industry and the process followed in this project. Specifications were provided prior to this project. The design must uniquely hold a load factor of 3.7 newtons and a torsional load of 0.5 newton meters. This is the preliminary design phase. This began by inputting values and equations into an Excel spreadsheet and calculating results for direct stress and strain. These were primary dimensions to begin with and were later amended during the design process. Equations were inputted using design specifications and known material properties provided. This is conceptual design phase 1. A first draft was developed using the primary dimensions in Excel. Following this, detailed design occurred and a rib was developed in SolidWorks using the primary dimensions. The spar was positioned in the rib by changing X and Y coordinates. A sample spar was then manufactured and tested. Changes were made to Excel to generate passes and meet the requirements. Material was limited to a 5mm thickness, so tripling the material used increased the spar thickness. A rectangular spar was settled upon to ensure passes and the final design was developed. A CAD drawing was created in SolidWorks and also a 3D model to represent the changes made in Excel. Assembly of the final design was created in SolidWorks and a 10-rib design was selected by the group. However, for ease of manufacture and limited time constraints, a 6-rib design was finally decided upon, and slots used in the ribs meant that the trailing edge would be easier to fit. Manufacture began by assembling individual components starting with the spar in its rectangular cross-section and increased thickness, then cutting the ribs, leading edge and trailing edge. Precision was used to ensure the spar would fit in the ribs. Once each component was developed, assembly of the final design began, and parts were joined with glue and tape was used for extra support. A simple flat leading edge and trailing edge were used and testing began. Torsional twist is the rotation of the component due to the applied load. It can be measured using the following method where delta H minus delta B is the vertical displacement minus the tip deflection at the load. The actual angle was 7.219 degrees but only 1.3 degrees was predicted. This may have been due to the clamp being loose, allowing greater rotation. Tip deflection was then calculated. The wing was clamped to the workbench and increasing masses were applied with the tip deflection measured at each mass. Failure occurred at 5.059 newton meters greater than 2.99 newton meters predicted. This may have been due to the glue and tape taking some of the stress and enabling a greater mass to be held. When the spar failed, compression failure was experienced near the wing root due to the clamp. Further improvements such as laser cutting parts would have made this design look more professional.